Quantum 1 tutorial question number 7. Okay, here we have a photoelectric effect emission experiment. A metal surface inside an evacuated tube was illuminated with light. So we have a light falling on a piece of metal surface. They repeat the experiment with different frequency of the light used, and for each frequency they measure the corresponding stopping potential, Vs. Okay, and question part A and part 1 and part 2. Just sub-definition. What's meant by the work function of a metal and what's meant by the stopping potential. Okay, work function, basically a metal contains free electrons, but to take the free electrons out from the metal surface you need some minimum energy. That minimum energy to remove the electron from the surface of the material is called the work function energy. And once the electrons are emitted, okay, the voltage, the opposing voltage needed to stop the electrons from reaching the collector plate is called the stopping potential. Okay, so stopping potential is the minimum retarding potential required to stop all the electrons from reaching the collector. Okay, B part 1. From this graph, deduce the Planck constant as well as determine the work function for this metal, and then give the answer in electron volts EV. Okay, for this graph is Vs against F. It's about photoelectric effect experiment. Okay, we need to invoke the equations that describe this whole photoelectric effect experiment, this concept, and this equation will be the Einstein photoelectric equation, okay, which is as follows. Okay, the stopping potential is going to be equal to h over E times frequency minus work function over E. So if you look at this equation, Vs, if you plot Vs as the y-axis and F as the x-axis, then the gradient will give you the h over E. H is the Planck constant and E is the electronic charge. So to find the value of the Planck constant h, all you do is just find the gradient of this graph. Okay, gradient of graph 7.0. So one point we take is this point 7.0 and 3.0. The other point we can take from here, or actually here, or here anywhere. If you take from here, maybe you can see, you can read this as maybe 1.3 or maybe 1.25. Okay, whenever you read from a graph, there's a margin of error. Okay, suppose we use 1.3, then that's the gradient. Then after we find the gradient, we just equate to h over E. Then from there, we will find the value of h. Okay, if you do that, you get h is approximately 6.6 times 10 to the power minus 34 joule second. Then part 2, determine the stopping potential. Okay, one thing from the graph, right? This value, this is the lowest frequency. This is the lowest frequency where you can produce electrons, emitted electrons. That's why you require some stopping potential. So this is the minimum frequency where you can produce electrons. Below that, there's no electrons emitted, so there's no need for any stopping potential. So from here, that will be threshold frequency. Then from the threshold frequency, we can calculate the work function. Okay, the work function is just simply phi, which is equal to h times f naught. Okay, another formula for the photoelectric effect equation. So we sub in h and we sub in the f naught. You can either read as 1.3 or 1.25. Okay, when you sub in, you get the answer 8.619 times 10 to the power minus 19 joules. But because the question wants your answer to be in EV, to convert joules in EV, all you do is just divide by E. So once you divide by E, that's how I convert joules to EV. Okay, in this case the answer is 5.4 EV. Okay, next. Part 3. If the electrons emitted from the metal constitute a current of 0.10 microampere, so given the current yes, we can find the number of electrons that's ejected and collected per second. Okay, rate means per second. Photoelectrons are referring to the electrons. It's just the electrons themselves. So they are asking for the number of electrons that's moving per second given the current. Okay, this comes from the earlier topic, the current of electricity topic. When you're given the current, yes, you can find the number of electrons per second for that current. Well, we have Q equals to IT. Q is the total charge that move, but the charge are made of electrons. So the charge is equals to the number of electrons times the electron charge. So I equals to QT is equal to NE over T. N over T is the number of electrons per second, is what we want to find. So just rearrange. N over T will be equals to I, bring the E the other side, become I over E. So the number of electrons per second, or the rate at which the electrons are ejected or collected, is equals to I over E. Okay, so you sub in the values, you get 6.25 times 10 to the power 11 per second. Okay, part 4. The stopping potential is 4.0 volts when a new instant light of frequency is used. Okay, we are told that they use a stopping, they have a stop, that when this frequency F, some frequency is used, they obtain a stopping potential of 4 volts. So from the graph, we can straight away immediately read off when the stopping potential is 4 volts, that corresponding frequency used is somewhere here about 2.25 times 10 to the power 15 hertz. So we can deduce that the frequency F they use is 2.25 times 10 to the power 15 hertz. Okay, then the next thing is they also tell us that 1 in 3 photons at this frequency succeeds in injecting a photoelectron. But early on, we have just calculated there are so many 6.25 times 10 to the power 11 electrons are ejected. And part 4, they are telling us that for every electron, there's correspondingly 3 photons. 3 photons for ejecting 1 electron. So since there are so many electrons, the number of photons will just simply times 3. So here n refers to the number of photons. Number of photons is 3 times 6.25 times 10 to the power 11. This is the number of photons. When you take number of photons times the HF, HF is the energy of each photon, and HF will give you the total energy of all the photons. Then total energy divided by time is the power of the light. So to find the power of the light, we just take the number of photons per second times HF. And there you have number of photons per second is 3 times the number of electrons, then times H times F. Okay, then there is the answer for the power of the light, 2.8 times 10 to the power minus 6 watts. Okay, next, part 5. Explain the observation that the graph in figure 7.1 does not extend below the horizontal axis. So notice that they give you the graph, they only draw the graph here, then they do not draw below. Well, this graph will not exist physically because if you use a frequency that's lower than a threshold frequency, you won't get any electron emission at all. Nothing happens. Nothing happens, so there's nothing to measure, no points to plot. So that's it. B part 5 is simply because nothing happened at the time. There's no emission of photoelectrons for frequency less than the threshold frequency. So there's no points here, so you don't draw any graph here. Okay, next. Suggest why the tube for part 6. If a different metal was used, okay, earlier on they used one metal, now they use, let's say, a different metal. When you use a different metal, there's one thing will change, the work function. Different metal has different work function. Because different metal, you need different energy to remove the electrons. Some metal, the electrons are easier to remove using less energy. then you have a lower work function, but some metal you require more energy to remove the electron, then that will have a higher work function. So if they use a different metal, the work function will be different. So if the work function is different, how would the graph change? Okay, we know that work function is related to the threshold frequency. The metal with a more higher work function, you require more energy to remove. Then you require photon that has more energy. Then in that case you require light of higher frequency, because energy of photon is proportional to the frequency. So once the work function has changed, the threshold frequency will be affected. That means the graph, the new graph, will now cut at a different x-intercept, reflecting different work function. So B part 6, the gradient, the intersect with the x-axis will be different, okay, because the threshold frequency has changed. Whereas the other feature, or the graph, there are two features, mainly is either x-intercept or y-intercept or the gradient. So let's talk about the gradient. Okay, as we see from the equation of the photoelectric effect, Vs equals to h over E f minus phi over E. The gradient is h over E. H is a Planck constant, E is an electronic constant. This constant never changed, that's why they call it constant. So the gradient is always the same regardless of what changes you do, because H and E doesn't change. So even when you change the matter, the gradient doesn't change. So B part 4, B part 6, the gradient doesn't change, but the x-intercept will change. Okay, B part 7 suggests, okay, this is something that you probably did not read it in the lecture notes, so they ask you to on the spot guess why the tube in this experiment needs to be evacuated. Evacuated means there's vacuum inside, no gas, no air inside the tube. So why do they want no gas or no air inside the tube? What happens in the tube? Okay, what happens is that inside the tube there are the emitter plates and the collector plates. Electrons are emitted from the emitter plate, and the electrons will then move to the collector plate. But if along the way inside the tube there are some gas or air molecules, okay, then these air and gas molecules will collide, okay, or rather the electrons that move through them will collide with the gas molecules. Then these electrons will get stopped, okay, along the way, if the tube is not evacuated. So if the tube is not evacuated, when you do the experiment, you won't get any, or you get very little current, very little electrons, because they are all stopped by the gas molecules themselves. So you won't be able to observe anything. So it's important that the tube will have evacuated, so that the electrons can freely travel to their collector. And also because we want to measure the K of the electrons by measuring the stopping potential, we want the stopping potential to stop the electrons rather than the air molecules to stop the electrons. So it's important that your tube must be evacuated to allow the electrons to reach the collector plate. And at the same time, if you have some gas molecules, then you will definitely introduce errors in the measurement of the stopping potential to measure the Ke. Okay, then B part 8. Also another suggest question. That means you probably didn't see this in lecture notes, or you have to read elsewhere, or on the spot you try to guess a possible reason. So they say that over time the work function of a certain matter will increase. Okay, notice that it's in air. We know that in the photoelectric effect experiment they always talk about clean metal surface. So it's important that the metal to be clean. Then you have the no other factors affecting the photoelectric effect. So what happens if the metal is not clean? That's what we can think, that probably what happens, the work function, the metal changes. So any metal that's left in the air, maybe they become dirt accumulated, or maybe you will gain some oxide because it's in contact with the air, surrounding air. So as you leave the metal inside the air, then over time you gain a layer of dirt or layer of oxide layer. Then this will affect the energy needed to remove the electrons from the metal surface, because if there's a layer, then extra obstacle to remove the electrons from the metal surface. So if you need more energy to remove the electron from the metal surface, that means the work function has increased. Okay, so that's B part 8. Okay, and that is question number 7.